Let's review one of the trickiest types of implicit differentiation problems. Let's say we want to find dy dx given cosine of x squared y equals e to the 2y plus tangent x. Well, first you have to recognize that you have to use implicit differentiation. And what I like to say is that the y is all up in there. So this is not just y equals some function of x. Y is really buried inside the equation, and there's actually multiple copies of y. So we want to start by finding d dx of both sides. So here's that operator d dx, not dy dx yet, d dx on both sides. Now the derivative with respect to x of cosine of x squared times y is going to require a chain rule and a product rule. So the derivative of cosine is negative sine, and then we'll leave the inside alone, x squared y, times the derivative of the inside is a product rule. X squared is one function and y is another function. I'm going to have a big bracket here, and then I'm going to go ahead and leave this first function alone. So I'm going to leave x squared alone, times the derivative of the second function. Well, the derivative of y with respect to x is just dy dx. We could also think the derivative of y is 1, and then with the chain rule, the derivative of y with respect to x is dy dx. Plus, now I'm going to leave that second function alone. I'm not taking its derivative, so I'm just going to leave it alone, y. And the derivative of x squared is 2x. That's just the derivative with respect to x of x squared is 2x. Okay, so that's the derivative of the left-hand side, and now the derivative of the right-hand side. So the derivative of e to the 2y. So we're going to take the derivative sort of as usual. So this would require the chain rule. A 2 is going to pop out of there from the derivative of the inside. So it's going to be like e to the 2y times 2, the derivative of the inside. But then because the variables don't match, basically we do, the regular standard derivative rule. But because the variables don't match, we have to put a dy dx. Technically, what we're doing is the chain rule. The derivative of that inside, 2y, wasn't just 2, it was 2 dy dx. And then the derivative of tangent x, these are added, so I could do each one separately. This is just going to be secant squared x. That part right there is really the calculus. From here, it is algebra. I need to go ahead and attempt to isolate dy dx. So this next step is going to be distributing this entire negative sign of x squared y to each term in here so that I can have terms that I can add and subtract to the other side. I'm going to have negative x squared sine of x squared y dy dx. Basically, we're just putting all of these factors next to each other. Don't do something crazy like put x squared into this sine function. Then we're going to have minus 2xy sine of x squared y is equal to 2e to the 2y dy dx plus secant squared x. And now we're going to combine like terms. We're going to subtract 2e to the 2y dy dx to the left, and we'll add the second term over here to the right after making some more space. All right, so I have negative x squared sine of x squared y dy dx minus 2e to the 2y dy dx. And then on the right-hand side, I already have secant squared x, and I'm going to add 2xy sine of x squared y. So I have the dy dx terms on the left. I can factor out that dy dx. And I'll have negative x sine of x squared y minus 2e to the 2y. And the right side stays the same. So the last step here is just dividing by this entire factor right here to get dy dx by itself. So we have dy dx is equal to, in the numerator, secant squared x plus 2xy sine of x squared y all over. Let's do two things at once here. There's a negative in each of these terms, so we'll factor the negative out of the entire thing, and we'll leave the denominator as positive x squared sine of x squared y plus 2e to the 2y. So there's this negative now in front, and this is going to be my final answer.